Welcome to episode 11 of the Semiconductor Age. In the previous episodes, we saw how semiconductor devices evolved into transistors, logic circuits, and eventually powerful processors. Today we explore the difference between CPUs and GPUs and discover how parallel computing changed the world of computing. Not every computational problem is the same. Some require a few powerful processors working sequentially, while others can be divided into thousands of smaller tasks that run simultaneously. A CPU is designed to handle complex and varied tasks. It has a relatively small number of powerful cores, making it excellent at sequential operations, decision-making, and running general-purpose software. A GPU takes a different approach. Instead of a few powerful cores, it contains a huge number of smaller processing units designed to perform many similar operations simultaneously. But what exactly do we mean by parallel computing? Imagine that you have 1,000 numbers and need to perform the same mathematical operation on every one of them. A sequential approach processes them one after another. A parallel approach divides the work into many pieces and processes those pieces simultaneously. So instead of asking one worker to do everything, we give the same task to many workers at the same time. Suppose we need to add two large arrays of numbers. Each addition is independent, so thousands of additions can happen simultaneously. This is exactly the kind of workload where GPUs become extremely powerful. GPU architecture is built around throughput. Instead of making every core extremely powerful, GPUs use large numbers of simpler processing units to perform massive amounts of parallel computation. So the difference is architectural. A CPU prioritizes flexibility and powerful individual cores, while a GPU prioritizes massive parallelism and throughput. Neither is universally better. The right architecture depends on the problem. GPUs were originally developed to handle graphics. Rendering an image means calculating enormous numbers of pixels, and many of those calculations can be performed independently. Parallel processing made GPUs ideal for this task. But researchers soon realized that GPUs could do much more than render images. If a problem could be expressed as many similar calculations, the same parallel hardware could accelerate scientific and engineering computations. This became especially important for artificial intelligence. Training modern AI models involves enormous numbers of matrix and vector operations, exactly the kind of parallel workload GPUs handle extremely well. The future isn't about choosing between the CPU and GPU. Modern systems use both. The CPU manages general purpose and sequential work, while the GPU accelerates highly parallel workloads. CPUs excel in operating systems, control logic, and complex sequential tasks. GPUs shine in graphics, simulations, scientific computing, machine learning, and other workloads where thousands of operations can run together. Parallel computing has transformed what computers can accomplish. From realistic graphics and scientific simulations to modern AI, the ability to perform enormous numbers of calculations simultaneously has become a foundation of modern technology. The deeper lesson is about architecture. Computing progress isn't simply about making individual transistors faster. It is also about designing smarter ways to organize them and use them together. From CPUs to GPUs, we've seen how parallel computing changed the way we build and use computers. If you found this episode useful, like, share, and subscribe to Physical Sciences Consultorium, PSC, and join us in episode 12, where we'll explore the AI chip and why artificial intelligence needs specialized hardware. Keep exploring, keep questioning, and keep discovering the physics behind technology.